Reflection property for the interval 0, $. Okay, let's begin with slide 1. Welcome. This slide serves as an introduction to a very useful technique for evaluating definite integrals. As you know, when we work with definite integrals, sometimes the integral we're presented with can be quite complicated to solve directly. Fortunately, there are certain properties that allow us to rewrite the integral in a different, and often much simpler, form. We're going to focus on one such property today, called the reflection property for the interval from 0 to a. We'll refer to it as property p subscript 4. Now, this property p subscript 4 is actually a specific case of a more general property, which we call the general reflection property, and we denote that as property p subscript 3. The key difference is this. The general reflection property, p subscript 3, works for any interval defined by limits a and b. However, property p subscript 4 is specifically designed for integrals where the lower limit of integration is 0. So, we're looking at integrals of the form, starting from 0 up to some constant value, a. Finally, and this is really important, this property is incredibly helpful when dealing with trigonometric functions, things like sine, cosine, and tangent. It allows us to use those handy complementary angle identities, you'll recall those from trigonometry, to simplify the expression inside the integral, making it much easier to evaluate. We'll see exactly how this works in the examples coming up, but keep in mind that simplifying the integrand is the main goal here. The mathematical statement. Okay, so let's move on to the core of this property. This slide formally states what we call the reflection property for the interval from 0 to a, which we've designated as property p4. It states that if you have a continuous function, we're calling it f of x, and this function is defined on the interval from 0 to a, then the definite integral of f of x with respect to x from 0 to a is equal to the definite integral of f of a minus x with respect to x, also from 0 to a. Let me break that down. The integral symbol, followed by f of x dx, represents the area under the curve of the function f of x. We're calculating this area between the limits 0 and a. Now, the right side of the equation says we can calculate the same area by integrating a slightly modified function, f of a minus x, between the same limits, 0 and a. Essentially, this equation is telling us that the integral of the original function is identical to the integral of a reflected version of that function. We'll see in the following slides why this is true. It's all about the area remaining constant even when we reflect the function. And as we move forward, you'll see how this seemingly abstract property becomes incredibly useful for solving definite integrals, especially those involving trigonometric functions. Remember, here is just a constant value defining the upper limit of our integration. Understanding the concept. Now, look at this slide. It asks us to visualize the function f of x, graphed between x equals 0 and x equals a. Imagine that curve on a coordinate plane. The key to understanding this property lies in what happens when we replace x with a minus x. Think of it like this. Replacing x with a minus x performs a reflection of the function across the midpoint of the interval from 0 to a. Let's pause for a moment. What is the midpoint of the interval from 0 to a? It's simply a divided by 2, or a over 2. So, we're reflecting the graph around the vertical line x equals a over 2. Now, why does this reflection not change the area under the curve? Well, consider that the definite integral calculates the area between the function and the x-axis. Whether you calculate that area by moving from left to right, that is, from 0 to a, or by traversing the same area via its reflection, the total area remains exactly the same. Essentially, we're just looking at the same region from a different perspective. Because the area under the curve is unchanged, the value of the definite integral also remains unchanged. That's why we can confidently say that the integral from 0 to a of f of x dx is equal to the integral from 0 to a of f of a minus x dx. Okay, so let's dive a little deeper into why this reflection property, property p4, actually works. As we discussed on the previous slides, this property is a powerful tool for simplifying definite integrals, especially those involving trigonometric functions. This concept will become even clearer as we move on to the next slides and see how to apply this property step by step with some concrete examples. But it's crucial to grasp this visual understanding first. The reflection preserves the area and therefore preserves the value of the integral. Step-by-step application process. Okay, so now that we've established what the reflection property for the interval from 0 to a is, that is, property P4, let's talk about how to actually use it. This slide outlines a step-by-step process. First, identify the limits. This might seem obvious, but it's crucial. We need to make absolutely sure that our definite integral has a lower limit of 0 and an upper limit of some constant, which we're calling a. Remember, this property specifically applies when you're integrating from 0 to a. If your limits are different, we'll need to use a more general approach, as we discussed briefly earlier. Next, substitute the variable. This is where the reflection happens. Take your original function, let's call it f of x, and replace every single x you see within that function with the expression a minus x. So, wherever you see an x, you substitute a minus x in its place. This is the core of the reflection property. Then, simplify using identities. After the substitution, you'll often have a new expression that looks a bit messy. This is where your algebra and trigonometry skills come in handy. Use any relevant identities to simplify the function f of a minus x. A common example, especially when dealing with trigonometric functions, is that the sine of pi over 2 minus x is equal to the cosine of x. Keep those identities in mind, as they'll often unlock the simplification you need. Finally, combine if necessary. This is a technique we'll see in more complex problems, and we'll start seeing it in the examples on the next few slides. Often, simply substituting and simplifying isn't enough to solve the integral directly. The trick is to add the original integral, which we often denote as I, to the transformed integral, the one we got after applying property P4. By adding them together, terms often cancel out, leaving you with a much simpler integral that you can easily solve. So, those are the 4 steps. Keep them in mind, and we'll walk through some examples to see how they work in practice. We'll start with a trigonometric example on the next slide, so you can see how these steps come together. Worked examples. Okay, let's move on to applying the reflection property we've just learned. This slide introduces our first worked example. Here, we're asked to evaluate a definite integral, and it's labeled as I. The integral is from 0 to pi over 2, that's written as integral from 0 to pi divided by 2 of the function sine of x, divided by sine of x plus cosine of x. So, we have sine x over sine x plus cosine x inside the integral. Now, remember from the previous slides, this integral has the form we need to apply property P4. We have a definite integral with a lower limit of 0 and an upper limit which is a constant, in this case, pi over 2. Also, the function inside the integral, sine x over sine x plus cosine x, is continuous within that interval. So, we're all set to use the reflection property to simplify this. In the following slides, we'll systematically apply the steps we discussed earlier, substituting, simplifying using trigonometric identities, and ultimately solving for the value of I. Keep in mind that the goal here isn't just to find the answer, but to understand how the reflection property helps us tackle integrals that might otherwise be quite difficult. We'll see how reflecting the function across the midpoint of the interval allows us to create a more manageable integral to solve. Example 1 continued. Now this slide shows us the first step in applying that property. It states, Step 1, apply property P4. Remember, property P4 tells us that the integral from 0 to a of a function f of x dx is equal to the integral from 0 to a of f of a minus x dx. In our case, a is pi over 2, so we're going to substitute x with pi over 2 minus x within our original integral. Let's look at what that gives us. We replace every instance of x in the integrand, that's the function we're integrating, with pi over 2 minus x. This gives us the integral from 0 to pi over 2 of sine of pi over 2 minus x, divided by sine of pi over 2 minus x, plus cosine of pi over 2 minus x, with respect to x. Okay, let's move on to slide 6. As you recall from the previous slides, we were tackling the integral I, which was the integral from 0 to pi over 2 of sine of x divided by sine of x plus cosine of x. With respect to x, we've established that the reflection property, property P4, is a powerful tool for integrals of this form. Essentially, we've transformed the integral using the reflection property. Now, in the next slide, we'll simplify this new integral using some trigonometric identities, building on what we've already learned. This is a crucial step, as it sets us up to leverage the symmetry created by the reflection property to solve for I. Example 1 continued. Okay, so let's move on to step 2, as outlined on this slide. Remember, in the previous step, we applied the reflection property, property P4, to our integral I. This gave us a new integral, the integral from 0 to pi over 2 of sine of pi over 2 minus x, all divided by sine of pi over 2 minus x plus cosine of pi over 2 minus x. With respect to x now, this looks a bit messy, doesn't it? That's where our knowledge of trigonometry comes in handy. We're going to use some standard trigonometric identities to simplify this expression. Specifically, we know a very useful identity. Sine of pi over 2 minus x is equal to cosine of x, and similarly, cosine of pi over 2 minus x is equal to sine of x. These are complementary angle identities, and they're crucial for problems like these. So, let's substitute these identities into our integral. Replacing sine of pi over 2 minus x with cosine of x, and cosine of pi over 2 minus x with sine of x, we get a much cleaner integral. This simplifies to the integral from 0 to pi over 2 of cosine of x, divided by cosine of x plus sine of x. With respect to x, notice how much simpler that looks. This substitution is the key to unlocking the solution. In the next step, we'll combine this new integral with our original integral, and you'll see why we did all this work. So, keep this simplified form in mind as we move forward. Example 1 continued. Okay, let's move on to step 3. As we discussed in the previous slides, the key to solving these types of integrals using the reflection property is often to combine the original integral with the one we get after applying the property. So, what we're going to do now is add the two forms of I together. Remember, I represents our integral, the integral from 0 to pi over 2 of sine of x divided by sine of x plus cosine of x. So, we write I plus I equals, and now we write out both integrals. The first one is the original integral, the integral from \text 0 to pi over 2 of sine of x divided by sine of x plus cosine of x $. And then, plus the transformed integral we obtained using the reflection property, which is the integral from 0 to pi over 2 of cosine of x divided by sine of x plus cosine of x. Now let's simplify this. Notice that we have a common denominator in both integrals, sine of x plus cosine of x. When we add fractions with a common denominator, we simply add the numerators. Therefore, I plus I becomes 2 times I, and the integral simplifies to the integral from 0 to pi over 2 of sine of x plus cosine of x, all divided by sine of x plus cosine of x. Essentially, the sine of x plus cosine of x terms in the denominator cancel each other out, leaving us with just one inside the integral. This is a huge simplification, and it's why the reflection property is so useful. In the next step, we'll see how easily this simplified integral can be solved. Example 1 continued. Okay, let's move on to step 4 of our example 1. As we've seen in the previous slides, we've skillfully manipulated the integral using the reflection property to reach a much simpler form. Now, we just need to evaluate it. So, here we have 2I equals the integral from 0 to pi over 2 of 1 dx. Notice how beautifully everything simplified. We're now integrating a constant function, which is just 1, with respect to x, from 0 to pi over 2. To solve this, we recall that the integral of a constant, in this case 1, is simply x. So, we write 2I equals x, evaluated from 0 to pi over 2. This means we substitute the upper limit, pi over 2, into x, and then subtract the value of x at the lower limit, which is 0. This gives us 2I equals pi over 2 minus 0, which simplifies to 2I equals pi over 2. Finally, to isolate I, we divide both sides of the equation by 2. This gives us our final answer, I equals pi over 4. And there you have it. We've successfully evaluated the integral using the reflection property. Remember, this technique is particularly useful when dealing with trigonometric functions, as we've demonstrated here. In the next example, we'll see how this property can be applied to a different type of trigonometric integral involving tangent functions. Example 2. Handling tangent functions. Here on the screen, we're asked to evaluate the definite integral, represented as I equals the integral from 0 to pi over 2 of 1 over 1 plus tangent of x with respect to x. Okay, let's move on to our second worked example. As you'll recall from the previous slides, we're using the reflection property P4, to tackle definite integrals. This time, we have a slightly different integrand, and it involves a tangent function. So, we have our integral I, and the limits of integration are from 0 to pi over 2. The function we're integrating is 1 divided by 1 plus the tangent of x now. As we discussed earlier, the key to applying property P4 is to manipulate this integral into a form where we can simplify it. We'll see how we do that in the following steps. Remember, the goal is to leverage trigonometric identities and the reflection property to make the integral easier to solve. We'll be adding the original integral to its reflected version, just like in our first example, to hopefully cancel out some terms and arrive at a straightforward solution. Example 2 continued. Okay, let's move on to slide 11. As you recall from the previous slides, we're working on evaluating the integral, I, which is the integral from 0 to pi over 2 of 1 divided by 1 plus tangent of x. With respect to x now, the first step in tackling this integral is to rewrite the function inside the integral. Currently, we have a tangent function in the denominator, and it often makes things easier to work with if we express tangent in terms of sine and cosine. So, we know that tangent of x is equal to sine of x divided by cosine of x. Therefore, we can substitute that into our integral. This gives us the integral from 0 to pi over 2 of 1 divided by 1 plus sine of x divided by cosine of x. With respect to x, to simplify this further, we can multiply both the numerator and the denominator of the inner fraction by cosine of x. This eliminates the fraction within a fraction. Doing so, we get the integral from 0 to pi over 2 of cosine of x, divided by cosine of x plus sine of x, with respect to x. This rewritten form is what we'll work with in the next step, where we'll apply the reflection property P4, that we discussed earlier. Notice how this new integral, while looking different, represents the exact same integral as the original one. We've simply rewritten the integrand in a more convenient form for applying our property. Example 2 continued. Okay, let's move on to step 2, where we apply property P4, the reflection property for the interval 0 to a. Remember, we're working with the integral, I, which is the integral from 0 to pi over 2 of 1 over 1 plus tangent of x, and we've already rewritten it as the integral from 0 to pi over 2 of cosine of x divided by cosine of x plus sine of x now. Property P4 tells us that the integral from 0 to a of a function f of x dx is equal to the integral from 0 to a of f of a minus x dx. In our case, a is pi over 2. So we need to replace every instance of x within our integrand, that's the part after the integral sign, with pi over 2 minus x. Let's do that. We get the integral from 0 to pi over 2 of cosine of pi over 2 minus x, divided by cosine of pi over 2 minus x, plus sine of pi over 2 minus x dx. Now, let's simplify this using our trigonometric identities. Recall that cosine of pi over 2 minus x is equal to sine of x, and sine of pi over 2 minus x is equal to cosine of x. Substituting these into our integral, we get the integral from 0 to pi over 2 of sine of x, divided by sine of x plus cosine of x, dx. Notice something interesting? This new integral looks remarkably similar to our original integral I. This is exactly what we want to happen when we apply property P4, as it sets us up to simplify the problem significantly. In the next step, we'll combine this transformed integral with our original integral to solve for I. Example 2 continued. Okay, let's move on to step 3 of example 2. As we've seen in the previous examples, and as outlined in property P4, a key strategy when dealing with these types of integrals is to combine the original integral with the one we obtained after applying the reflection property. So, we're now going to add the original integral, which is integral from 0 to pi over 2 of cosine x divided by cosine x plus sine x dx, to the transformed integral we just found, which is integral from sine x divided by sine x plus cosine x dx. When we add these together, we get 2 times I equals integral from 0 to pi over 2 of cosine x divided by cosine x plus sine x dx, plus integral from 0 to pi over 2 of sine x divided by cosine x plus sine x dx. Notice what happens when we combine the fractions under the integral sign. The denominators are the same, so we can simply add the numerators. This gives us 2 times I equals integral from 0 to pi over 2 of cosine x plus sine x, divided by cosine x plus sine x dx. Essentially, the terms cosine x plus sine x in the numerator and denominator cancel each other out, which is exactly what we were hoping for. This simplification is the power of the reflection property. It allows us to manipulate the integral into a much more manageable form. In the next step, we'll see just how manageable it becomes. Example 2 continued. Okay, let's finish up this second example. This is step 4, final calculation. As you can see, after combining the integrals in the previous step, we've simplified the expression to 2 I equals the integral from 0 to pi over 2 of just 1 with respect to x, so we have 2I equals integral from 0 to pi over 2 of 1 dx. Now, to solve this, we simply integrate 1 with respect to x. Remember that the integral of a constant, in this case 1, is just x. So, we write 2I equals x, evaluated from 0 to pi over 2. The square brackets indicate that we're evaluating the expression at the upper and lower limits of integration. This means we substitute the upper limit, pi over 2, into x, and then subtract the value of x at the lower limit, which is 0. This gives us 2I equals pi over 2 minus 0, which simplifies to 2I equals pi over 2. Finally, to isolate I, we divide both sides of the equation by 2. This gives us I equals pi over 4. So, the value of the original integral, the integral from 0 to pi over 2 of 1 over 1 plus tangent of x dx, is pi over 4. And that concludes our second example. Remember, the key to these problems is recognizing when to apply the reflection property, manipulating the integral, and then cleverly combining the original and transformed integrals. In the next slide, we'll discuss some common mistakes students make when working with this property, so pay close attention to those to avoid them in your own work. Common mistakes to avoid. First, it says incorrect substitution. A very frequent mistake is substituting x with x instead of a minus x. Remember, the core idea of this property is reflection. We're not simply negating the input, we're reflecting it across the midpoint of the interval. So, when we apply property P4, the substitution must be the upper limit, that a value minus x. This ensures we're correctly mirroring the function. Next, we have ignoring the limits. This is crucial. Property P4, as we've defined it, only works when the lower limit of integration is 0. If your integral doesn't start at 0, for example, if it's from 1 to you can't directly use property P4. In such cases, you need to employ the more general reflection property, which we referred to as property P3. It states that the integral from to b of a function f of x is equal to the integral from to b of f of a plus b minus x. Don't mix these up. Finally, forgetting to add I. This is a bit of a trick that often appears in more complex problems. After you've applied property P4 and obtained a transformed integral, you might find that simply evaluating either the original or the transformed integral doesn't lead to a solution. The key is to add the original integral, which we often denote as I, to the transformed integral. This addition often cancels out complicated terms, simplifying the integrand and allowing you to solve for I. Think of it as a strategic step to unlock the solution. Okay, let's move on to slide 15. This slide highlights some common pitfalls students encounter when applying the reflection property, property P4, that we've just learned. Paying attention to these will save you a lot of frustration. So keep these 3 points in mind as you practice, and you'll be well on your way to mastering the reflection property. Now, let's move on to the final slide where we'll summarize the key takeaways. Key takeaways. First, let's look at the formula. It states that the integral from 0 to a of a function f of x with respect to dx is equal to the integral from 0 to a of f of a minus x with respect to dx. Essentially, this is the core relationship we've been working with throughout these slides. Remember, this is property P4, a specific case of the more general reflection property. Next, the purpose of this property. It's a powerful tool for simplifying integrands. That's the function inside the integral sign. It's especially useful when dealing with trigonometric functions like sine x, cosine x, and tangent x, particularly when we're integrating over the interval from 0 to pi over 2. We saw this in action in our examples with the trigonometric fractions. Now let's talk about the core logic. Imagine the graph of your function f of x, stretching from x equals 0 to x equals a. When we replace x with a minus x, we're essentially reflecting that graph across the midpoint of the interval. Think of it like a mirror image. The crucial thing is that this reflection doesn't change the area under the curve. The area remains the same, whether you calculate it directly or from its reflection. That's why the integral's value stays constant. Finally, the strategy. When you encounter a definite integral with limits from 0 to a, and it looks particularly complicated, especially if it involves a complex fraction with trigonometric terms, this is where you should consider applying property P4. Remember the key step we often used. After applying the property, we would add the transformed integral to the original integral. This often leads to cancellations and a much simpler integral to solve. Okay, let's recap everything we've learned about the reflection property for the interval from 0 to a. This is our final slide, and it's designed to solidify the key takeaways. So, keep these points in mind, practice applying the property, and you'll find it to be an invaluable technique in your calculus toolkit.